Hi, I'm Henry Townley from Rye Country Day School, and I'm going to be presenting our solution to the wake angle problem. So, according to Lord Kelvin's theory, the wake angle of an object traveling on the surface of the water is surprisingly independent of the object itself. So that means the angle stays constant, or it stays at the same degree, no matter how fast the boat moves, or no matter what kind of object we're using. And so what I'm going to do over the course of this presentation is explain why that wake angle stays constant according to Lord Kelvin's theory, identify the limitations of that theory, and then I'm going to compare our predictions to experimental data. So here are just a couple brief visuals of what a water wake looks like. When I use the term wake, I'm referring to the interference pattern caused by the dispersion of surface water waves. Then the wake angle is the angle between an object's or the boat's trajectory to the line beyond which the surface of the water is unperturbed. According to Lord Kelvin's theory, that angle, the wake angle, should be a constant 19.47 degrees. So most of the assumptions we need to make are actually pretty standard assumptions made for fluid mechanics problems, but the last one is particularly important for our case. After the water has been disturbed by the boat, we assume the only forces acting on the wake are gravity and surface tension. So before we dive into wake theory, we first need to explore the concept of dispersion. So in a dispersive medium where there is dispersion, different frequencies f travel at different phase velocities v sub p, and then the envelope of the superposition of these waves travels at the group velocity v sub g. Now the relationship between a frequency and its phase velocity for a particular medium is given by what's called a dispersion relation, and we actually have the dispersion relation here for deep water gravity waves, and that's omega squared equals gk. And when we apply the definitions of phase velocity and group velocity, we find out the group velocity is equal to exactly 1/2 of the phase velocity in this medium, and this is going to turn out to be an essential part of the constant Kelvin wake. So now let's take a step back and assume for a moment that water is a non-dispersive medium where there is no dispersion. And this problem in this case would be actually really simple because all the waves emitted from the boat would actually travel together and result in a shock wave or a Mach cone. And in a Mach cone, the group velocity is equal to the phase velocity, so the angle of the wake, right here given by phi, is directly dependent on boat velocity. But water is not a non-dispersive medium. Water is a dispersive medium where there is dispersion and every frequency has its own Mach angle. There's a geometric approach proposed at Crawford, which is probably the most intuitive way to see how this results in a constant wake angle. So you can see here in this diagram that we have a boat moving from B1 to B2, and then you have a narrow band of frequencies propagating in the direction of point W. And so by the time our boat gets to point B2, the phase of the wave, of the emitted wave, which travels at the phase velocity, gets to point W. But we actually can't see anything moving at the phase velocity. The visible disturbance that we can actually see moving on the surface of the water is traveling at the group velocity. And since group velocity is 1/2 of phase velocity, that visible disturbance we see arrives at point G in the same time. And now if we were to include this same narrow band of frequencies moving in the same direction, but at every point from B1 to B2, then you could extend this disturbance along the B2, along the line B2N, and you would have a wake-like disturbance there. But things actually get a little trickier because when we consider that each angle or each narrow band of frequencies that we consider has a different angle at which the group wave propagates. But if we were to vary the angle of the phase wave front, we actually see that the angle of the group disturbance reaches a maximum at 19.47 degrees, as you can see here by the line B2G2 at the diagram on the right. And so here there's actually constructive interference because the group waves with frequencies just larger or smaller than this dominant frequency, as shown by lines B1, BW, and B1, B3. The group wave fronts actually propagate at almost the same angle, and so you have constructive interference. And beyond this dominant wake angle, there is no group disturbance and the surface is unperturbed, and so this is therefore our wake angle. So at the right here you can see a summation of a narrow band of frequencies that we made using MATLAB. The individual frequencies are traveling at speeds given by deep water dispersion, and when we superimpose them, as we've done here in the bottom right hand corner, you can see a disturbance traveling at the group velocity. This graphical summation here corresponds to the line B1W here, and that disturbance you see over here corresponds to the point G in the graph at the left. But the actual wake we see moving in the water is the addition of all these disturbances over a wider band of frequencies traveling in every direction. So now, in order to prove that the angle of this constructive interference, or our wake angle, does not depend on boat velocity, according to Lord Kelvin's wake theory, we need to find the wake angle theta as a function of boat velocity, phase velocity, and group velocity. And so after we substitute in the values for phase and group velocity, we find the theta at each boat velocity for which d theta is equal to 0. And this corresponds to the wave number for the frequency corresponding to the maximum group disturbance angle over the wake angle. We then plot boat velocity as a function of wake angle. And as you can see, the wake angle remains at a constant 19.47 degrees for every boat velocity. But gravity is not the only force at work. Surface tension and water depth can also be relevant factors in certain scenarios. And it's when we incorporate all three of these factors into our dispersion relation, as I've done up here at the top, that we discover the limitations to Lord Kelvin's constant wake angle theory. So the first angle in which we find a limitation of Kelvin's constant wake angle theory is in shallow water, where the depth of the water d is much less than the wavelength of the dominant frequency lambda. If we were to neglect surface tension, as I've done on the left over here, then phase velocity turns out to equal group velocity, and then there is no dispersion. Therefore, the wake acts like a Mach cone and not like a Kelvin wake. But if we were to neglect surface tension for deep water, as I've done on the right over here, where water depth is greater than the dominant wavelength, we arrive at the deep water gravity dispersion relation, which we examined earlier. So then the next situation in which Kelvin theory doesn't hold occurs at low object velocities. In order to examine velocities between 0 and 0.5 meters per second, we need to take both gravity, both gravity and surface tension into account in our dispersion relation. At the right, we have expressions for phase and group velocity, and the equations for so phase, group velocity, and then the expression for wake angle, which we used earlier. And then when we when we make a couple substitutions, we arrive at this rather ugly-looking equation here, and then when we apply the same process of finding theta, when d theta dk is equal to 0, you can then plot boat velocity as a function of wake angle, and as you can see, the wake angle actually decreases significantly for boat velocities less than 1 meter per second. Then, finally, we come to what seems like a limitation at the far end of the spectrum where velocity is greatest. So when a boat exceeds its hull speed, it actually seems as if the wake begins to decrease again as velocity increases. And this is because at the hull speed, the dominant wavelengths being emitted from the boat are equal to the length of the boat. And as a result, the wake coming off the front of the boat starts to interfere with the wake coming off the back of the boat. And so here's actually where we need to make an important distinction between the wake angle and the angle of maximum amplitude as defined in a paper by Darman and Raphael in 2013. So while the wake angle, which is shown above here in red, is the angle beyond which the surface is unperturbed, the angle of the maximum amplitude, shown here in blue, is the angle along which the disturbance has the greatest displacement from the surface level. According to the theory of Darman and Raphael, the Froude number, which is a relationship between boat velocity and boat length, can be used as an indicator for when these two angles will deviate from one another. In scenarios in which the Froude number is greater than 0.5, the wake angle stays constant according to Kelvin theory, but the max amplitude angle, which we often misconstrue as the wake angle, is inversely proportional to the Froude number, and so decreases with decreasing velocity. So overall, I have identified two object parameters, velocity and length, in three different situations that lead to inconsistencies with the Kelvin wake theory. In shallow water, the water wake will always act like a Mach cone, and the angle will decrease as velocity increases. In deep water, we actually transition between three different regimes with a unique wake behavior on each, and it depends on the boat velocity. And so, at low boat velocities, where surface tension is the dominant force, we actually have the wake actually acts like a Mach cone and decreases the angle decreases as the boat velocity increases. At the in-between velocities, the wake actually will be constant, as Lord Kelvin predicted. And at velocities beyond the whole speed, which is dependent on boat length, and which we would visibly interpret as the wake angle, decreases. However, the true wake angle, which is the angle beyond which the surface is unperturbed, stays constant. So now we move on to our experiments to see if our theory holds up in practice. Our experimental trials included measuring the dispersion relation in a tank of water we had set up in our physics classroom. Then we measured wake angles in 12 centimeter water with varying object speeds and lengths. And then finally we measured wake angles in shallow water. Our first step was to examine how different frequencies behaved in our particular experimental setup and to construct an experimental dispersion relation. And to do this, we actually set up a ripple maker at the surface of our water, and we set this ripple maker to different frequencies, and then we measured the wavelengths being produced. And at the right, you can see that our measured dispersion relation, which is in blue, most closely models the dispersion relation, which includes only gravity at low wave numbers, and it most closely matches the surface tension model at higher wave numbers. And so here in the bottom right, you can actually see the same data plotted against different variables. As you can see, at low frequencies matches the gravity model, and at high frequencies it matches the surface tension model. And so then what we did is we actually worked backwards using the wavelength, and we tried to match the wavelengths to different dispersion relations. And as you can see, our data most closely matches the theory when we assume that the dispersion relation includes both gravity and surface tension, as we've done in the purple over here. And so therefore we can justify including the terms for the two forces in our dispersion relation, and we can also justify neglecting shallow water effects for the frequencies tested. So here we move on to the next phase of our experiment, in which we ran different objects along the surface of the water in a 12 centimeter deep tank, which we set up in our physics classroom. And so here you can actually see two frictionless tracks that we set up, and along these tracks we ran carts to which we attached the object that we were testing the wake of. And so then we also had a pulley system, as you can see over here, to reduce the remaining effects of friction. And then we tried to remount the camera as high as possible above the tank in order to limit distortion effects. So here you can see a variety of the wakes that we produce experimentally. In our analysis, we actually choose to focus on boat length, boat velocity, and water level, because these were the parameters that were most relevant according to our theory. This graph summarizes the results that we obtained in 12 centimeter deep water with a thin metal pole that had a 1 centimeter diameter. And so what we did is we ran the pole through the water at different velocities, and we measured the wake angle that was produced. And so here you can see that the wake angle, the max amplitude angle, decrease at low velocities where surface tension is dominant, as you can see here at the left. But because our object here is such a short hull length, only 1 centimeter, the object actually reaches hull velocities at very, very low velocities. And so the max amplitude angle continues to decrease even as surface tension becomes less relevant at around 0.6 meters per second. But as velocity increases and gravity becomes dominant, the actual wake angle, which is shown here in yellow, plotted in yellow, remains relatively constant and is consistent with the predicted value of 19.5 degrees. In this trial here, we used a styrofoam boat with a hull length of 16 centimeters, so quite a deal longer. With this hull length, the boat only reaches hull speeds at 0.6 meters per second, so it reaches hull speeds at faster speeds. And so you would expect to see both the wake and the maximum amplitude angle remain constant for a certain range of boat velocities in between where surface tension is dominant and in between where the Froude number takes over. But unfortunately, this is not entirely apparent in our data because of the limited size of our experiment. If we really wanted to conclusively test the effects of exceeding hull speed on wake angle, we would have needed a boat length with a hull length of at least, we would have needed a boat with a hull length of at least 40 centimeters that didn't reach hull speeds until around 1 meter per second, where surface tension would have been negligible. A larger and deeper tank would have also been needed in this case to accommodate the larger boat and to rule out the possibilities of shallow water effects at higher velocities. Finally, here we have the results of data taken in shallow water, so in water that was less than 0.5 centimeters. Here we can see that the wake clearly acts like a Mach cone and decreases with increasing boat velocity, and so therefore the wake angle is definitely dependent on boat velocity. In conclusion, we were able to demonstrate the dependence of wake angle on boat velocity in shallow water and at low velocities in deep water where surface tension is dominant. However, we could not conclusively substantiate our wake angle theory at higher velocities beyond the hull speed and beyond that critical Froude number of 0.5. So here are just a couple of the references that we used. Thank you so much for watching.